everybody. We're getting ready to do lesson 2.2 of pre-calculus today. And 2.2 is polynomial and rational functions, part 1, using transformations to sketch graphs of polynomial function, as well as using the leading coefficient test to determine end behavior of graphs. And this lesson has 26 points here of classwork, 0 points in notebook taking. And we'll start out with our bell work teachers. This is the bell work for today. Monthly revenue in thousands of dollars from sales of a digital picture frame is approximated by this function here, where P is the price per unit in dollars. Find the monthly revenues for unit prices of $50, $70, and $90. And then B, find a unit price that will yield a maximum monthly revenue. Give your students about 6-7 minutes for this. Okay, welcome back for our solutions to our today's bell work. And for number 1, here are our prices here for when P equals 50, and in this situation here, price per unit is $50. We have a gross revenue here of 54, 61, and 61.2 for 61.6 and 61.2 for these prices here. And then the unit price that will yield a max, so negative B over 2A, negative B over 2A, and that yields $79 would be a maximum revenue price there. So that is your bell work. Okay, moving right along into our first slide here. Graphs of polynomial functions. This will be on your classwork, students. Graphs of polynomial functions. At this point, you should be able to sketch accurate graphs of polynomial functions up to the second degree polynomial functions. So, f of x equals a is a line. This is a line of slope a. This would be slope-intercept form of a line. And then a parabola. This is your equation that describes a parabola. And then the graph of a polynomial function is continuous, meaning that when you sketch it, your pencil won't leave the paper. So that'd be a continuous here. This is not a continuous function. It has a gap here in your function, so it is not a polynomial function. And then they have smooth curves. Polynomials have smooth curves, and they won't have this. This looks like an absolute value function here, possibly. So a polynomial function of degree n has a form of this kind of form where your coefficients decrease or in a descending order from left to right, as well as your exponents. Where n is a positive integer and a to n cannot equal 0. Polynomial functions have the simplest graphs are monomials if the form of f of x equals x to the n, where n is an integer greater than 0. The greater the value of n, the flatter the graph near the origin. When n is even, the graph is similar to the graph of f of x equals x squared and touches the x-axis at the x-intercept. When n is odd, it's similar to the graph of f of x equals x cubed and crosses the x-axis at the x-intercept. Polynomial functions of the form f of x equals x to the n are often referred to as power functions. So a cubic function, the basic characteristic of the parent cubic function is this here. This is your x cubed kind of like shape here of your classic cubic function. And the domain is negative infinity to positive infinity. Same thing for your range. Your intercept is at the origin, and it's increasing from negative infinity to positive infinity. It's an odd function. We'll get into that later. And it is the origin it's symmetric to the origin. Okay, example 1, library of parent functions, f of x equals x cubed. So we're going to sketch these functions here. So in this situation, A, f of x equals x cubed, the graph of g is obtained. So up here, g of x equals the negative x cubed. So the negative of x cubed is obtained by a reflection in the x-axis as shown. So instead of going up like this is x cubed, this is negative x cubed, like this. And then for f of x equals x cubed, the graph of h with respect to f of x equals x cubed, the graph of h, which is here, is obtained by a vertical shift of 1 unit upwards. So you just shift upwards here 1 unit, and you get this graph right here. From this is the parent here, and then this is the shift here. And then for C, we have a horizontal shift now to the right of 1 unit. So instead of it intercepting here at the origin, it intercepts the x-axis here at 1, 0. So x minus 1 cubed, this will be the shape of that graph. Okay, into our guided practice and then our independent practice. Sketch the graph of y equals x cubed and the graph of the function f describe the transformation. So x minus 2 cubed, here is our transformation. Then down here, this is your students, describe your transformation there. And this is your solution box here. Okay, so for our guided practice, here is our graph here of this transformation. Here's the parent. So we're moving horizontally to the right 2 units. And there's a horizontal shift of 2 units to the right of y equals x cubed. So do this one, students. Okay, the leading coefficient test, whether the graph of polynomial eventually rises or falls, can be determined by the polynomial function's degree, even or odd, and by its leading coefficient, as indicated in the leading coefficient test. As x moves without bound to the left or to the right, the graph of the polynomial function, and again it's in this order here, descending coefficients and descending exponents, without bound to left or right, eventually rises or following manner. So when n is odd, you have this situation here. And then if the leading coefficient is negative, it moves basically in a negative manner here with your right side of your graph heading down. Here, when n is odd and it's positive, the right side of the graph moves upwards. And then when n is even, if the leading coefficient is positive and it's even, then you get this like bump in the center and then it moves up. Although where this dotted line is, it means that this is a generalization. There can be other idiosyncrasies within that graph. And then here, if the leading coefficient is negative and a to the nth is less than 0, so if it's negative, both left and right will head in a negative direction. And this is classwork. This is a good classwork here. So on to example 2, applying the leading coefficient test. Use the leading coefficient test to describe right hand and left hand behavior of this graph here of this function. So because the degree is odd, we have a odd degree, and the leading coefficient is negative, the graph rises to the left. It starts up here, but from left to right, it moves generally in a negative manner like that. So it is falling on the right-hand side of the graph. Okay, our next guided practice, leading coefficient test. We have this function here, and this is yours, students, your independent practice here. Use a graphing utility to verify. So we're going to describe what this function will likely do. And then here's our solution box. This is what you should write your responses in, your descriptions. Okay, so for number 3, it has a degree 4. Here's our degree. The leading coefficient is 2. Degree is even, and the leading coefficient is positive. Therefore, the graph rises to the left and the right. So it kind of has a bump in the center, and both sides of the graph lead in a positive direction. Let me go right into another example here. Example 3, applying the leading coefficient test. Okay, applying the leading coefficient test. Use the leading coefficient test to describe the right hand and left hand behavior of the graph of each polynomial function. So here is our first polynomial. Because the degree is even, we have a leading exponent here of 4, and the leading coefficient is positive. This is positive 1. The graph rises to the left and right. So it would be, this is the graph of this polynomial right here. That's what it looks like. It looks like a W, almost. And then for B, x to the 5th minus x, because the degree is odd, we have a 5th degree polynomial, and the leading coefficient is positive. Its general movement is to left to right is positive, moving in a positive manner. But it doesn't have this because it's an odd degree, so it has this bump in the center and it goes down back up again. So that's the general shape of that kind of polynomial. Okay, so we're going to apply the leading coefficient test to these now. This is the guided, and then students, this is yours. So, and then here's your response box here. Let's do our guided here first. So in this situation here, degree is 2. Here's our degree. And the leading coefficient is -3. The degree is even, and the leading coefficient is negative. So we have an even degree with a negative coefficient. The graph, therefore, will fall to the left and to the right. So it'll be like this. It'll come up like this, have a bump like that, and then fall again down to the well. Okay, zeros of polynomial functions. It can be shown that for a polynomial function, and this is classwork, f of degree n, the following statements are true. 1, the function f has at most n real zeros. So the meaning it intercepts the x-axis n times. And then 2, the graph of f has at most n-1 relative extrema, meaning a minimum or a maximum, relative min or relative max. It has n-1. So the real zeros are polynomials. If f is a polynomial function and a is a real number, then the following statements are equivalent. X equals a is a 0 of the function. X equals a is a solution of the polynomial equation. X minus a is a factor of the polynomial. And then a 0 is an x-intercept of the graph of f. So here are some things that you can kind of hang your hat on, so to speak, about a polynomial function, how it's going to behave just by looking at it without even graphing. So let's go into an example here. Example for finding zeros of a polynomial. Find all real zeros of this here. So an algebraic solution is we're going to factor the thing. So we're going to factor out an x, and then we come with x cubed minus x squared minus 2x. Substitute 0 for f of x. We're going to solve for 0. And then we're going to factor out an x, and then we end up with this second degree polynomial now. Now we can factor that, and we get this here, x minus 2x plus 1. So after we've done that algebraically, we can say, so the real zeros are x equals 0, x equals 2, and then x equals negative 1. And the corresponding x-intercepts are 0, 0, 2, 0, and then negative 1, 0. We can get that from factoring, and then we go back and see if these are actual solutions. We put them back in, and they all check as solutions. So now the graphical solution, to solve it graphically, uses zero, a root feature of a graphing calculator, to verify these zeros. And then when we do that, we come up with this graph here. And sure enough, these are our solutions, negative 1, 0, 0, 0, and then 2, 0. These are solutions for our function right here. Okay, so guided practice, find zeros algebraically. B, use a graphing utility. And then C, use the graph to compare with part A. So we're going to solve algebraically first, and then we're going to use the graph to check our algebra. So here's our solution box. So to solve this algebraically, first we can factor out a 3, and then we get this quadratic here. And then we can use the good old quadratic formula to find our solutions to this quadratic. And then we get this solution here, 2 plus or minus square root of 3. And then when we graph it here, we get this here, plus or minus square root of 3 is 1 point something. So we get this here, that would be a subtraction. And then when we add the square root of 3 to 2, this would be our other solution there. So here are our solutions here, 3.732 and then 0.268. So that looks about right. You can use your trace feature on your graphing calculator to check these. And that's 2.2 part 1 of pre-calculus. Thank you very much.